So, we will continue for some more examples. Let us see the power function y equal to x to the power n, where n equal to 1. So, when you take n equal to 1, it is really y equal to x function. Earlier we did is the identity function, but now on the whole of real line. So, it is the straight line y equal to x. That is how it will look. When you take n equal to 2, it is y equal to x square. That is the second one, which looks like a parabola now, y equal to x square. At 0 it is 0, at 1 it is 1, at 2 it is 4, at minus 1 it is 1, at minus 2 it is 4, and so on. It is a parabola. If you take x cubed and plot it, maybe with a graphing calculator or in the computer, so you would see the graph would look like this, y equal to x cubed. So, there is some portion here which is matching with the x axis, it is not really matching, it is really joining with 0. Before 0, if it is less than 0, then its value is also less than 0. Similarly, if it is greater than 0, its value is also greater than 0, but it is a bit flat like the x axis at 0. So, the graph is plotted like this. At 0 only it touches here, crosses the y axis, again it goes. Now, come to y equal to x fourth, it will also look like this, but it is not like your x square parabola, it is a bit flatter here at 0 again. However, if it is smaller than 0, then it is not 0. Again, if it is slightly bigger than 0, it is not also 0, at 0 only it is 0. And if you take y equal to x to the power 5, it is similar to x cubed, but it is a bit more flatter. So, that idea we will see how it is coming more flatter, or what is the meaning of that. Right now it is nonsense. Okay, so, y equal to x to the power 5 would look again something like y equal to x cubed. This is the plot if you see. Now, let us take some more examples, say the power function with n equal to minus 1. So, you would get the function as y equal to 1 by x, which we have seen earlier. It is not defined at 0, except 0 everywhere else it is defined. So, it will look something like this, and its domain does not include 0, and its range also does not include 0, right, but all positive, all negatives, everything is there, right. So, it is range is r minus 0, domain is also r minus 0, as we have discussed earlier. Its graph will look like this and a hyperbola. Then if you take n equal to minus 2, you would get y equal to 1 divided by x square. Again at 0 it is not defined. So, domain excludes this 0, and range now cannot be negative, because it is 1 by x squared, which is greater than 0 always, because x is never 0 here. 1 by x can also never be 0. So, range is really all positive real numbers, and the graph would look something like this. At negative, at positive, they have the same value. So, it will look something this way, y equal to 1 by x square. So, let us take some rational powers, the fractional powers. Suppose you take the power function y equal to x to the power a, where a is some fraction like this, 1 by 2, 1 by 3, 3 by 2, 2 by 3. We will give some 4 examples here. How do they look, just to have the feeling. So, a equal to 1 by 2 gives you y equal to square root of x, and that has domain, as we know, is non-negative real numbers. Range is also non-negative real numbers, and it looks like this. At 0 again it is 0. If you take y equal to 1 by 3, a equal to 1 by 3, you would get the function y equal to cube root of x. Now, if you go to x equal to y cube, y to the power 3, and look it different way, that take the horizontal as y, just to rotate it 90 degrees. The graph y equal to x cubed and y equal to cube root of x look similar now. If you rotate it, it will be giving x equal to y equal to x cubed curve, right. So, this is you go to the y axis, think of you are going along this, and this is the vertical one, okay, turning from south to north x. then it would look something like this. And in this way, if you take x to the power 1 by 3, it looks a bit flatter. S curve looks like a bit flatter. Okay. So, let us take a equal to 3 by 2, y equal to x to the power 3 by 2, or it is really square root of x cubed. So, if you plot it, it would be looking like this. Its domain is again non-negative real numbers, range is also non-negative real numbers, and it looks something like one portion of a slightly looking like a parabola, but not. Now, come to x to the power 2 by 3, it is cube root of x squared. So, it would come this way, meet at 0 and again going this way. So, again its domain is the whole of real numbers, because cube root is defined for everything, and the range is of course 0 is included, and it lies above the x axis, all positive real numbers including 0, all non-negative real numbers. So, now let us look at very simple ones which are also useful, say polynomial functions. So, where we write a polynomial as a0 plus a1x plus a2x square plus anx to the power n, where these coefficients are given for a particular polynomial. Like you say y equal to 1 plus x square. So, they are a0, a1, a2, all of them are 1. So, this is a generic one, where these a0, a1, a2, these are real numbers, they are called the coefficients of the powers of x. So, now this n can be 0, so when n is 0, you get the constant function f x equal to a0. If n is 1, you get a straight line y equal to a0 plus a1x, and so on. So, let us see some graphs. The highest power of n is called the degree of the polynomial. So, degree is 0 means constant, degree is 1 means linear, degree is 2 means quadratic, and so on. So, the first one gives a cubic. A cubic generically looks like this, starts from this way and this way, where the coefficient of x cubed, that is the degree 3, is positive. So, it would look something like this. Y equal to x cubed by 3 minus x square by 2 minus 2x plus 1 by 3. If you do, it goes like this. It becomes 0 somewhere between 0 and 1, becomes 0 somewhere between minus 2 to 1, close to minus 2, and again between 3 to 4, close to 3. So, you can factor and check it. Now, let us see a quartic polynomial or degree 4. So, it looks something like this. It has again 0, it vanishes here minus 1 and between 0 to 1 and again near 2. So, this is how a degree 4 polynomial looks like. We take another which is really degree 7, x minus 2 to the power 4, x plus 1 to the power 3 into x minus 1. So, that again looks this way. These are all graphs drawn in the computer. Okay, just to have the feeling how do they look like. Let us see a rational function. A rational function is the ratio of two polynomials. So, here p x is a polynomial, q x is a polynomial. So, we have the function f x equal to p x by q x. Naturally, this rational function will not be defined when for all those x where q x equal to 0, because we cannot divide by 0. So, except those points, its domain will be everything else, that is the whole of real numbers minus the zeros of q x. For example, here y equal to 2x square minus 3 divided by 7x plus 4 is not defined for x equal to minus 4 by 7, except that point it is defined everywhere else. Okay. So, its graph also looks like a hyperbola. They are a bit tricky, they can change shapes, they are not very uniform like the polynomials, the rationals. So, division is there. So, it looks something like this. And this line which you see in the pink vertical line, it really meets the curve at infinity. That is why we have written it. It meets at 2 points, here on the down and also on the top. So, they are called asymptotes, but we will be talking, we are talking very much in advance now. We will be coming to that slowly after some time. So, finding the asymptotes or where the straight line meets the curve will give some idea about the shape of the curve. Let us look at the second one, y equal to 5 x square plus 8 x minus 3 divided by 3 x square plus 2. So, that is now a curve which looks something like this. Look at the blue lines. It is no way connected to the second one, first one we had seen, because the q x is 3 x square plus 2 now. So, it is x square. If it is not defined, it will be x square will be minus 2 by 3, which is not possible in reals. So, it is defined for our real numbers. Its domain is the whole of real number. You can't see any gap here. There you are looking at some gap, minus 4 by 7. It is not defined, but here there is nothing. For every real number it is defined. So, similarly, if you take the third one, 11 x plus 2 divided by 2 x cubed minus 1. So, 2 x cubed minus 1 can be 0, where when x cubed equal to 1 by 2 or cube root of 1 by 2. So, except those point, at that point everywhere else it is defined, and that is how it looks. Okay, these are something about the rational functions. In fact, all of these are called algebraic functions. So, algebraic functions are those which are obtained by adding, subtracting, multiplying, dividing, or taking roots of polynomials and so on, using those things. So, rational functions are special cases of that. Here are some other plots: y equal to x to the power 1 by 3 into x minus 4, y equal to 3 by 4 into x square minus 1 to the power 2 by 3, and y equal to x into 1 minus x to the power 2 by 5. Okay, so maybe we should try some problems now. So, as I told, sometimes we will just give the formula for f x and try to see what could be the domain where this function can be defined, and then what could be the range. So, for example, here is one. We are asked to find the domain and the range of this function, which is given by a formula f of x equal to 1 divided by 1 plus square root of x. So, first thing we should find out where it is not defined and then see what happens. And it is not defined when root x equal to minus 1, but root x cannot be minus 1. Can it be? Because root by definition has to be non-negative. So, that is not, that is ruled out. But then once root x is there, so this x has to be non-negative. That is exactly the domain. So, domain equal to non-negative real numbers here, and at x equal to 0 we also get y equal to 1, and y is in the range, means y must be equal to 1 divided by 1 plus root x, and we know that x is greater than 0, or if x equal to 0, y equal to 1. That case we have taken out first. So, let us take the second case when x is bigger than 0. Now, in this case we have to observe something: as x increases, y now decreases because it is 1 by y, but it remains positive. So, it cannot go beyond this 1. Therefore, the range must be 0, 1, but whether it is equal to that, you have to see something more, that for each y in the 0, 1, closed 1, open semi open interval, you should find a corresponding x, and that is quite easy to get. So, this is the range. Similarly, here in the second problem we are asked to find the domain and range of f x equal to 1 divided by square root of 4 minus x square. So, here again 4 minus x square has to be greater than or equal to 0, but also it is 1 divided by, so it cannot be equal to 0. So, this must be greater than 0. Now, if you factor it, 4 minus x square is 2 minus x into 2 plus x. So, this must be bigger than 0, and for which x this is bigger than 0, we would find that for every x which is between this minus 2 to 2, this is bigger than 0. You can check it, say minus 2 and 2 is our open interval. If x is anywhere here, then 2 minus x So, it is 2 minus x, this one it is positive, and 2 plus x, that is also positive. So, this is bigger than 0. It is really helpful to write in this form. If you take two numbers a and b, you see x minus a into x minus b will be positive once x is here, because x minus a is positive, but x minus b is negative, then you would get to be less than 0 if it is inside this. Now, using this same heuristic, you can write this as x minus 2 with a negative sign into x minus minus 2. So, x minus 2 into x minus minus 2 will be remaining negative if it is between minus 2 to 2, and there is a negative sign here. So, it is positive when it is within that. That will be easier to apply. So, the range should be equal to minus 2 to 2 open interval. The domain should be equal to minus 2 to 2 open interval. Then what should be the range? For that we may have to observe something more. So, the smallest value can be half. You can see, check from that by inspection, and then f x gets larger and larger as x increases, but it can increase only up to 2, not more than that, and it gets larger and larger as x decreases to minus 2 also, right, because it is that factor 2 minus x into 2 plus x. So, both the way it is decreasing, the range cannot go beyond half, cannot go below half. So, it has to be half closed, that is greater than any number bigger than half, and also can be equal to half, because at 0 it is equal to half. Therefore, the range is half to infinity, where half is closed. That is how it would look like. Let us check one more example. Say point P in the first quadrant lies in the graph of the function f x equal to root x. So, if you know f x equal to root x graph, then express the coordinates of P as functions of the slope of the line joining P to the origin. We are asked to find the coordinates of P. So, P will be a point, say a comma b, there are two numbers here. These should be expressed as functions of the slope of the line joining P to the origin. So, a point on that curve if you take, you have the origin. So, slope of this line, we will be taking this line, slope of that line tan of this theta. We have to express these coordinates at some functions of this slope. That is what is being asked. Okay, so, let us say P is a point on the curve which looks like x root x. So, what is the slope of the line joining P to the origin? y2 minus y1 divided by x2 minus x1, that gives you root x minus x. So, that is 1 divided by root x, and only x has to be greater than 0, because root x is there anyway, not the origin. Thus, P equal to x root x, which we can write now as, because m equal to 1 by root x slope, we can write as 1 divided by m square and 1 by m. So, that is the answer. Okay. So, let us look at the next problem. It asks to plot this graph of the function which is defined by mod x plus mod y equal to 1. It is really an equation. So, that means we want to find out all those points satisfying this equation mod x plus mod y equal to 1, and we have to really plot this set of all x y such that mod x plus mod y equal to 1. So, at some places it will be a function y equal to a function of x, but in total it may not be a function, like your circle. So, how to go about it? Let us look at some points. So, when x is 0, y can be 1 or minus 1, and when y is 0, x can be 1 or minus 1. So, our points on this are minus 1 0, 0 minus 1, 1 0 and 0 1. If you take the square with these vertices, it looks something like this. Okay. This is your 1 0, this is minus 1 0, and this is 0 minus 1, this is 0 1. If you take any point here, then that also satisfies mod x plus mod y is less than 1. But if you take any point on this straight line, that again satisfies mod x plus mod y equal to 1. That is what it is. Okay. So, it is really the square joining these at the vertices. These points, 4 points are the vertices of this square. Okay. So, let us stop here.